You know, when people ask me about the great paradoxes of physics, they often expect me to speak of something distant and abstract, something that belongs only in the realm of mathematics and arcane symbols. But the truth is quite different. The paradox that shook physics to its very foundations, the one that occupied my mind for decades and continues to challenge our deepest intuitions about reality, is something far more intimate. It concerns the very act of observation itself, the relationship between what we see and what exists, between the observer and the observed. It is a paradox that emerged not from speculation, but from the hard facts of experimental results, and it forced us to reconsider everything we thought we knew about the nature of matter, light, and reality itself. Let me take you back to the beginning of the 20th century, to a time when physics seemed on the verge of completion. The great edifice of classical mechanics, built by Newton and refined by generations of brilliant minds, appeared unshakable. Maxwell had unified electricity and magnetism into a single elegant framework. We understood heat, motion, gravity. The universe seemed to be a great clockwork mechanism, deterministic and knowable. If you knew the position and velocity of every particle at one moment, you could, in principle, calculate the entire future and past of the universe. This was the world I inherited as a young physicist. But there were cracks in this beautiful picture, small anomalies that most preferred to ignore. One of these concerned the nature of light itself. Now, this question had troubled physicists for centuries. Newton believed light was made of particles, little corpuscles traveling through space. But in the early 19th century, experiments by Thomas Young and others seemed to settle the matter definitively. Light behaved as a wave. Young's double-slit experiment was particularly convincing. When you shine light through two narrow slits onto a screen, you don't see two bright lines as you would if light were made of particles. Instead, you see an interference pattern, alternating bands of light and dark. This is characteristic behavior of waves. When two water waves meet, they can reinforce each other or cancel each other out, creating exactly this kind of pattern. Light, we concluded, must be a wave propagating through some medium, which we called the luminiferous ether. Then came the work that would begin to unravel everything. In 1900, Max Planck, in an act of what he later called desperation, proposed something radical to explain the spectrum of light emitted by hot objects. He suggested that light could only be emitted or absorbed in discrete packets, which he called quanta. The energy of each quantum was proportional to the frequency of the light. This was a mathematical trick at first, something Planck himself didn't fully believe. But it worked. It explained the data perfectly. 5 years later, a young patent clerk named Albert Einstein took Planck's idea seriously and applied it to the photoelectric effect. When you shine light on certain metals, they emit electrons. Classical wave theory predicted that the energy of the emitted electrons should depend on the intensity of the light. Bright light should produce energetic electrons, dim light should produce weak ones. But experiments showed something different. The energy of the electrons depended on the color of the light, its frequency, not its brightness. Blue light produced energetic electrons even when dim, while bright red light produced nothing. Einstein explained this by saying that light actually comes in particle-like packets, photons, each carrying an energy proportional to its frequency. An electron absorbs a single photon and is ejected with energy determined by that photon's frequency. This was revolutionary. Light, it seemed, had particle properties after all. So we found ourselves in a curious position. Sometimes light behaved like a wave, showing interference and diffraction. Sometimes it behaved like a stream of particles, photons interacting individually with matter. This was our first taste of what would become wave-particle duality. And it was deeply unsettling. How could light be both wave and particle? These seemed like mutually exclusive categories. A wave is spread out in space, a particle is localized. Yet the experimental evidence for both was irrefutable. But the real shock, the paradox that would truly shake physics, came when we discovered that this duality applied not just to light, but to matter itself. In 1924, Louis de Broglie made an audacious proposal in his doctoral thesis. If light, which we thought was a wave, can behave like particles, perhaps matter, which we knew to be made of particles, could behave like waves. He proposed that every particle has an associated wavelength, inversely proportional to its momentum. For large objects, this wavelength is impossibly small, undetectable. But for tiny particles like electrons, it might be measurable. Within a few years, this prediction was confirmed. Clinton Davison and Lester Germer in America, and George Paget Thomson in Britain, fired beams of electrons at crystals and observed diffraction patterns, the unmistakable signature of wave behavior. Electrons, the fundamental constituents of matter, were exhibiting wave properties. This was no longer just about light. The wave-particle duality extended to everything. Now, here is where the paradox becomes truly profound. Consider again the double-slit experiment, but this time with electrons instead of light. You fire electrons one at a time toward a barrier with two slits. On the other side, you have a screen that records where each electron arrives. What do you observe? If electrons were simply particles, little billiard balls, you would expect them to go through one slit or the other and create two bands on the screen corresponding to the two slits. But that's not what happens. Instead, even when you send the electrons through one at a time, so slowly that only one electron is in the apparatus at any given moment, you gradually build up an interference pattern on the screen, the same pattern you would get with waves. Think about what this means. Each single electron somehow interferes with itself. It's as if the electron goes through both slits simultaneously, like a wave would, and the two resulting wave components interfere with each other. But when the electron hits the screen, it always arrives as a single localized point, like a particle. We never detect half an electron or a spread-out wave on the screen, only a discrete impact at a specific location. Yet the pattern of where these impacts occur over time shows the characteristic interference bands of a wave. Now comes the truly mystifying part. Suppose you decide to find out which slit each electron actually goes through. You set up detectors at each slit to record when an electron passes. What happens? The interference pattern disappears. When you observe which slit the electron goes through, it behaves like a classical particle. It goes through one slit or the other, and you get two bands on the screen, not an interference pattern. But when you don't observe which path it takes, you get the interference pattern, suggesting it went through both slits. This is the paradox that shook physics. The very act of observation changes the behavior of the system. When we don't look, the electron behaves like a wave, going through both slits and interfering with itself. When we do look, it behaves like a particle, going through one slit. The electron seems to know whether we're watching it, and changes its behavior accordingly. This is not a failure of our measuring instruments, or a matter of disturbing the electron with our measurement, though that plays a role. It's something deeper. The electron genuinely doesn't have a definite path until we measure it. Before measurement, it exists in a state that somehow encompasses both possibilities simultaneously. This led me to what I called complementarity, one of the central principles of quantum mechanics. Wave and particle are complementary descriptions of reality. They're like two sides of a coin. You can look at heads or tails, but never both simultaneously. The wave and particle aspects of quantum objects are both real, both necessary for a complete description. But they're mutually exclusive in terms of what you can observe in any single experiment. Which aspect you see depends on what question you ask nature, what kind of measurement you perform. I spent countless hours debating these ideas with Einstein, my dear friend and intellectual sparring partner. He found this picture deeply troubling. God does not play dice with the universe, he famously said. Einstein believed that quantum mechanics, despite its tremendous success in making predictions, was incomplete. He thought there must be hidden variables, some deeper level of reality we hadn't yet discovered, which would restore determinism and remove the apparent randomness and the strange role of observation. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published a paper presenting what they saw as a fatal flaw in quantum mechanics. They described what we now call the EPR paradox, after their initials. They imagined two particles that have interacted and then separated by a large distance. According to quantum mechanics, these particles can be in an entangled state, where their properties are correlated even though either has a definite value until measured. For instance, they might have opposite spins, but neither has a definite spin direction until you measure one of them. Here's the puzzle. Suppose you measure the spin of one particle and find it pointing up. Instantly, you know the other particle's spin is pointing down, even though it might be on the other side of the galaxy. Einstein argued that this was absurd. Either the information traveled faster than light between the particles, violating relativity, or the particles had definite spins all along, and quantum mechanics simply didn't describe these hidden properties. He thought this proved quantum mechanics was incomplete. My response was that Einstein was still thinking in classical terms. He was assuming that particles have definite properties independent of measurement. But this is precisely what quantum mechanics denies. The two particles, even when separated, are not independent systems. They're part of a single quantum state, and you cannot describe them separately until a measurement breaks their entanglement. The measurement on one particle doesn't send a signal to the other. Rather, the measurement outcome for one particle is correlated with what you'll find for the other because they're part of this unified quantum state. I remember telling Einstein that it was wrong to think we could separate the behavior of atomic objects from the interaction with the measuring instruments that define the conditions under which the phenomena appear. In the quantum realm, we cannot maintain the classical distinction between the object being observed and the apparatus doing the observing. They form an inseparable whole. This was a radical break from classical physics, where we assumed objects had definite properties regardless of whether we measured them. This brings us to what might be called the measurement problem, though I hesitate to call it a problem because I think it reflects a misunderstanding of what quantum mechanics tells us. In classical physics, measurement simply reveals a pre-existing property. The moon is there whether or not anyone looks at it. But in quantum mechanics, before measurement, a system exists in what we call a superposition of states. Schrödinger's famous cat thought experiment, proposed by Erwin Schrödinger in a spirit of skepticism similar to Einstein's, illustrates this strangeness. A cat is placed in a box with a quantum device that has a 50% chance of releasing poison. According to quantum mechanics, before you open the box, the quantum system is in a superposition of having released the poison and not having released it. Does this mean the cat is simultaneously alive and dead? Schrödinger meant this as a reductio ad absurdum, showing that quantum mechanics leads to absurd conclusions when applied to everyday objects. But I would say this misses the point. The cat is not a closed quantum system. It's constantly interacting with air molecules, photons, and countless other particles in its environment. These interactions effectively constitute continuous measurement, causing what we now call decoherence. The cat is always in a definite state of alive or dead, not because quantum mechanics doesn't apply to large objects, but because large objects are constantly being measured by their environment. The strange quantum superpositions persist only for carefully isolated microscopic systems. The real lesson is that quantum mechanics describes not reality as it is independent of us, but reality as it reveals itself through our interactions with it. The wave function, that mathematical object that contains all the information about a quantum system, doesn't directly represent physical reality. It represents our knowledge, the potential for different measurement outcomes. When we measure, we gain information, and the wave function collapses to reflect this new knowledge. This interpretation troubled many of my colleagues, and it continues to trouble people today. They want to know what's really happening between measurements. Where is the electron when we're not looking? Does it truly go through both slits, or does it go through one and we simply don't know which? I would say these questions are based on a false premise. They assume that microscopic objects have the same kind of existence as macroscopic ones, that they're always in some definite state whether we observe them or not. But quantum mechanics teaches us that this assumption is wrong. The electron doesn't have a definite position between measurements. It's not that we don't know where it is, it genuinely doesn't have a definite position. Position only becomes meaningful in the context of a measurement. This might sound like philosophical wordplay, but it has concrete consequences. The Heisenberg uncertainty principle, discovered by my young colleague Werner Heisenberg, is not just about the limits of measurement precision. It's a fundamental feature of reality. You cannot simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely you determine one, the less precisely you can know the other. This isn't because our instruments aren't good enough. It's because a particle doesn't have definite simultaneous values for position and momentum. These quantities are complementary. An experiment designed to measure position precisely will necessarily be an experiment that doesn't measure momentum precisely, and vice versa. I found Heisenberg's principle to be perfectly compatible with my principle of complementarity. Different experimental arrangements revealed different complementary aspects of reality. You can design an experiment that treats an electron as a particle and measures its position. Or you can design one that treats it as a wave and measures its wavelength, which is related to momentum. But you cannot design a single experiment that simultaneously does both with arbitrary precision. The experimental setup itself determines which aspect of reality reveals itself to you. Now, I want to address something that often gets misunderstood. When I say that observation affects reality in quantum mechanics, I don't mean that human consciousness plays a special role. Some people have taken the quantum measurement problem to suggest that mind or consciousness collapses the wave function. I never endorse such a view. By observation or measurement, I mean any physical interaction that creates a record, that amplifies the quantum event to the macroscopic level where it becomes irreversible. This could be a photographic plate registering an electron, a Geiger counter clicking, or countless air molecules scattering off an object. Consciousness is not necessary for this process. The paradox, the real deep paradox, is that we find ourselves needing two different descriptions of nature. For the macroscopic world of our everyday experience, classical physics works beautifully. We can predict the motion of planets, design bridges, build machines, all using Newton's laws. But for the microscopic world of atoms and subatomic particles, we need quantum mechanics with its probabilities, superpositions, and complementarity. These two descriptions seem incompatible. Classical physics is deterministic, quantum mechanics is probabilistic. Classical objects have definite properties at all times, quantum objects exist in superpositions. Yet both must somehow be descriptions of the same underlying reality. The resolution I proposed is that there's no sharp dividing line between the quantum and classical realms. Rather, classical behavior emerges from quantum mechanics when systems become sufficiently large and complex, and when they interact sufficiently with their environment. The process of decoherence, which I glimpsed but which was only fully understood by later generations, explains how quantum superpositions give rise to the definite classical world we experience. But this emergence doesn't eliminate the quantum foundation. Classical physics is an approximation, valid in certain limits, but quantum mechanics is fundamental. This brings me to reflect on the nature of scientific understanding itself. Before quantum mechanics, we thought the goal of physics was to describe nature as it is, independent of us. We were trying to discover the objective reality behind our perceptions. But quantum mechanics suggests a different view. Physics describes our interaction with nature, the patterns we find in our observations. The insistence on a description of reality independent of observation is a metaphysical prejudice, not a requirement of science. What we can know, what we can talk meaningfully about, is limited to what we can observe and measure. This sounds like a retreat from the ambitions of classical physics, and in a sense it is. We give up the dream of perfect prediction, of complete knowledge of an objective reality existing independently of observation. But in return, we gain a framework of extraordinary power and scope. Quantum mechanics has been tested to incredible precision across an enormous range of phenomena, from the behavior of individual atoms to the properties of materials, from the structure of molecules to the functioning of lasers and transistors. It works. Not sometimes, not approximately, but with stunning accuracy and universality. The paradox that shook physics, the wave-particle duality and all that follows from it, forced us to grow up intellectually. We had to abandon certain intuitions about reality that seemed self-evident but were actually just extrapolations from our macroscopic experience. We had to accept that nature at its most fundamental level is stranger than we imagined, that it doesn't conform to the categories we inherited from everyday life. I'm sometimes asked whether I believe quantum mechanics is the final word, whether some future revolution might overthrow it as quantum mechanics overthrew classical physics. I doubt it. I think quantum mechanics has revealed something genuinely fundamental about the structure of reality. Future theories might encompass quantum mechanics in some larger framework, just as quantum mechanics encompasses classical physics as a limiting case. But I expect the core insights, the complementarity, the role of measurement, the probabilistic nature of predictions, these will remain. What continues to fascinate me, even now, is how quantum mechanics forces us to be more careful and precise in our language. In classical physics, we could be sloppy, using words like position and momentum without carefully specifying under what conditions these concepts apply. Quantum mechanics demands precision. We must specify the experimental arrangement, the measurement context, before we can meaningfully assign properties to a system. This is not a weakness but a strength. It's a recognition that scientific concepts gain their meaning from the operations we perform, the experiments we conduct. I devoted much of my later career to exploring the implications of quantum mechanics beyond physics. I wondered about the lessons it might teach for other fields, for biology, for psychology, for understanding human knowledge more broadly. The idea of complementarity, that a complete description might require mutually exclusive perspectives that cannot be captured simultaneously, seemed to me to have broader application. In biology, mechanistic and vitalistic perspectives might be complementary. In psychology, thoughts and feelings cannot be observed simultaneously with the same precision. These extensions are speculative, of course, and must be approached with caution. But the central lesson seems to me quite general. The observer and the observed cannot be separated. Our descriptions of reality are necessarily descriptions of our interaction with reality. The young physicists today build quantum computers, explore quantum cryptography, investigate quantum entanglement with a technical sophistication I could hardly have imagined. They manipulate individual quantum states with exquisite control. Yet the foundational questions remain. What is the nature of the quantum state? What happens during measurement? How does the classical world emerge from quantum foundations? These questions are as alive now as they were in my time, though we have new tools and new insights to bring to bear on them. I'm often portrayed in historical accounts as having won the debate with Einstein about quantum mechanics. But I never saw it as a debate to be won. Einstein's questions were profound and legitimate. His discomfort with quantum mechanics pushed me to articulate more clearly what the theory was saying, what it meant. Science advances through such creative tension, through the clash of different perspectives and the struggle to reconcile them or to understand why they cannot be reconciled. The paradox that shook physics was not a logical contradiction to be resolved by cleverness. It was a genuine surprise about the nature of reality. Something that couldn't have been predicted from pure thought but had to be discovered through experiment. We found that nature simply doesn't work the way we intuitively expected. Particles are not little billiard balls. Waves are not ripples in a medium. Reality at the quantum level is something different, something that exhibits aspects of both waves and particles depending on how we choose to look at it, but is ultimately neither. This forced humility upon us. We cannot trust our intuitions when venturing into domains far from everyday experience. The microscopic world of atoms doesn't operate according to the rules we abstract from watching objects fall and planets move. We must be guided by experiment, by mathematics, by careful reasoning, not by what seems obvious or natural based on our limited direct experience. Yet there's something beautiful in this realization. The universe is richer and stranger than we imagined. It doesn't conform to our preconceptions, and that's wonderful. It means there's always more to discover, always deeper questions to ask. The paradox that troubled us so much in the early decades of the 20th century opened up entire new territories of understanding. It led to technologies that have transformed civilization. It revealed fundamental limits to knowledge that have philosophical implications far beyond physics. When I look back on my career, on the decades I spent grappling with these questions, I'm struck by how much we learned and how much remains mysterious. We built a theoretical framework that works magnificently for making predictions. We can calculate the energy levels of atoms, the properties of materials, the behavior of particles and accelerators. But the interpretation, what it all means, remains contentious. Different physicists prefer different ways of thinking about it, different interpretations of the formalism. Perhaps there's a lesson in that too. Perhaps the mathematical structure is what's fundamental, and the interpretation, the story we tell ourselves about what's happening, is always somewhat arbitrary, a human overlay on the mathematics. But I cannot fully embrace that austere view. I believe in the reality of atoms, of electrons, of photons, even if they don't have all the properties we classically assumed. I believe quantum mechanics is telling us something true about the world, not just giving us a calculating device. The challenge is to understand what it's telling us, to find the right words, the right concepts, to express truths that seem to slip through the mesh of classical language. The paradox that shook physics ultimately shook our conception of what it means to understand nature. Understanding is not about constructing mental pictures that match reality like a photograph. It's about finding the right mathematical structures and knowing how to connect them to observation and experiment. It's about accepting that some questions don't have answers, not because we're ignorant, but because they're not well-formed questions in the first place. It's about recognizing that the observer is not separate from the observed, that the act of measurement is an interaction that helps to create the reality we measure. This is my legacy, or part of it. Not a final answer, but a new way of asking questions, a framework within which to think about the deepest puzzles of existence. The paradox that shook physics became the foundation of a new physics, one that is still unfolding, still revealing new wonders. And that, I think, is as it should be. The goal of science is not to reach a final destination but to continue the journey of discovery, always pushing further into the unknown, always willing to have our most cherished assumptions challenged by what we find there. The quantum world taught us humility, precision, and wonder. These are lessons I hope will endure long after the specific debates of my era are forgotten, long after new theories have emerged to deepen and extend what we began.